move DNS great. There is and this is a general purpose strategy. It works for SSH. It will work for Tor. It'll work for everything. It stops DNS leakage. There's a little bit of a problem. So in 2004, so this is DNS over SSH. I already did SSH over DNS. That means I have DNS over SSH over DNS. Yes, I have finally implemented DNS over DNS. Malkovich. For committing such a sin. I believe this is Cinnamon Toast Crunch and Mickey's. I'm going to go crawl under this table. Holy crap. Actually, it's pretty good now that I think about it. Yeah, you got to get that Cinnamon Toast Crunch aftertaste in. Then it's rocking. All right. Thanks to Zane Lackey. He thought I wouldn't. So, more bugs. More stuff with SSH. You log into a box. Haven't logged into this particular box before. And it says to you, I don't recognize the key fingerprint of this box. Do you recognize 09B199841777DB8? What the hell? Is there anyone in this room who's going to remember this? Really? I'll quiz you on it later. I will buy all your drinks for the night if you can remember that in 3 hours without writing it down right now. So, now according to the design for SSH, yeah, you are actually supposed to recognize this hideous blob of hex. And you're supposed to reject it if it looks unfamiliar. I mean, I'm serious. They will tell you this with a straight face. So there's something called the 2 billion SSH key attack. The hacking group ADM came up with it. And it's very simple. They generate 2 billion keys and spoof the key that looks the most similar. And it works like a freaking charm. We need something better. So, funny little research field called cryptonamonics. Why have I called it that? Because the name is awesome. So, cryptonamonics. There are the study of remembering crazy crypto crap. All right. So there's 3 classes of human memory, at least to the degree that's useful in cryptography. Rejection, I've never seen that before. Like, I've never seen 09A9B1, yes or no. Recognition, it's that one, not the other one. I've definitely been drinking that. I should have been drinking that. And then there's recollection. Let me describe to you the Mickeys and I'm having trouble recollecting Cinnamon Toast Crunch. All right. So all SSH requires out of us for this particular use is rejection. All we need to be able to say is that string of hex is not it's not the string of hex you're looking for. Hex is a total failure. So what else do we have available? Well, there have been some other attempts. Using abstract art patterns. There's actually a really cool thing called passfaces that got used. And the idea is that you would recognize, oh yeah, it's this blob of pixels, or that's sort of okay. But these faces, the face stuff actually works really well. We have hardware acceleration to deal with human faces. Great stuff. It actually is very interesting. You can get a very specific form of brain damage, and then you just can't recognize faces. Everyone looks like they have the same face. That's that hardware dying, actually. The problem is that the amount of entropy we get out of these systems is pretty low. Let's say you have this grid of 9 faces, and you have to match 5 of them. So you have to match the right face. I recognize that girl, and that girl, and that guy, that girl. Yeah, you only get like 59,000 possibilities there. That's less than 16 bits of entropy. This is fine. This is great for an online authentication system, which is, of course, what Passface is built. It doesn't at all work for offline. So I couldn't go and represent this sequence of characters as a bunch of faces and expect anything to work out of it. It just wouldn't work. That instead of making 2 billion SSH keys, I'm going to make 59,000 not going to take too long. So we need better than that. So humans don't remember arbitrary strings of characters effectively. We know this, right? We do remember stories. Homer's Iliad has a ridiculous amount of entropy in it in terms of what we remember from these stories passed down through eras and eras and eras. However, stories have a very unique element to them. They kind of sort of change over time. You know, things get added, things get removed, things get forgotten, things get inserted. The most stable element of a story are the names of the participants. Humans have a ridiculous amount of memory for human names. This is just, it's part of our acceleration. What if we turn these hideous sequence of bytes into a series of human names? So what I did, this is bizarre, but it does work. Take this data. Notice that there's a little bit more unique female names than male names, way more last names than either. What we're going to do is we're going to take 512 male names, 1,024 female names, and 8,192 last names. That's going to be 9 bits of entropy, 10 bits of entropy, and 13 bits of entropy. Sum 32 bits. We are going to pick these names according to names that are the most different as possible. Bob and Bobby are very similar. Remembering the difference between the two is kind of hard. Bob and Jim, much different. So what we want to do is we want to try to calculate the greatest differences between all the names because we want you to be able to recognize the difference between Bob and Jim. And what we're going to use is something as an edit distance metric, like Python's Levenshtein algorithm, or it's not from Python, but it's implemented in Python. And we're going to try to prevent two names from looking or sounding similar. And what we're going to do is we're going to take that big blob of hex and we're going to represent it as a series of names. And it will actually, this has actually been implemented. It ends up looking like that big blob you saw earlier became Julio and Epifania de Zudi, Luther and Roland Dornbos, Manuel and Twyla Imbesi. Now, you'd say, this is a lot of names to remember. It turns out you don't have to recollect them off the top of your head. You just need to see them and go, oh yeah, I've seen that name before. This works. You need to see them every single time. They can't just pop up like, oh, have you ever seen this before? And it's only showing up when there's a problem. No, you need to see it every time you log into a box. But if you see these names every time you log into a box, you actually start associating these people with the box you're trying to log into. It works.
Are we as good at remembering the order that those 5 sets of names come in?
Excellent question. Here, grab a beer. Dealing with order problems sucks. What's interesting is I'm estimating about maybe 8 to 10 bits of rot from the fact that Julio might be at the top or might be at the bottom. Julio might actually be married to Roland instead of Epifania, things like that. So there is actual potential for shuffling. So I wouldn't want to see this for really, really, really short hashes. The point is with hashing algorithms that you have so much extra capacity. Now, it is possible, and this is going off on a bit of a tangent, but it is an awesome question because it's totally what I've been looking at. It is possible to actually embed additional bits. So there'd be yet another series of names that's just there to handle the fact that there's bit rot. Say there was a 6th couple that was added. That was just basically a hash of the particular orderings of the rest. You'd have 160 bits, and then the fact that the human brain can shuffle them a bit, you add extra bits to compensate based on what we do or don't pay attention to. That may actually be useful to do. This is also new for Toorcon. Name-based passwords. How many people here have ever had to log in where you actually have to have password standards and they have to meet certain entropy requirements? Awesome. How many people here have ever had a password like lowercase a, lowercase l, 7, $13, lowercase n, uppercase m? Okay, these are a pain in the ass. You end up with things like 23 syllables, and you have to describe them slowly, and there's typos, and you're screwed. Oh, yeah, there's a bug in the slide. Have a beer. What if, instead, you typed Dirk and Kolapagio, Omar and Gina Heimel? Okay, so you're typing a heck of a lot more. You get more entropy, because in this case, in the previous example, you had 48 bits of entropy. These two names give you 60. You have more entropy, less syllables to describe it, and you have the possibility for spell check while typing in a password. I'm not convinced this is going to be a better way to log into systems, but if you actually have a high security environment that requires you to have 64 bits of entropy in your password, this may be a better way to do it. And the really cool thing is this can be entirely client-side. You could potentially map an arbitrary password, just your client will convert Dirk and Kook to 7 AL7 whatever. Go ahead.
Have a beer?
Yes. That works well once. I have one beer left.
L isn't X. Huh? L isn't X.
No, it's not. But if you consider A through Z, lowercase, A through Z, uppercase, 0, 9, and a group of, what's it called? And a group of the most common punctuation, you end up with about 64 combinations. So what you could do is you could basically just write a mapping function between the characters that actually get used in passwords, even for secure passwords, and Dirk and Kolapagio. Then what you'd have is you'd have, say, one of the characters is basically an escape bit, where it's, hey, guess what? Some jackass used a piece of the password that we couldn't represent in the normal 64, and here now we're going to put in the raw ASCII code. Is that you take your arbitrary plaintext password and you just map the characters to a sequence of bits, and then that sequence of bits gets remapped to names. Does that make sense? All right, go ahead.
We did something like this for passphrase encrypted hard drives. We actually then wrote the tool because we forgot the passphrase. We wrote a tool based on which to go through and attack our passphrase. And we use that, so we defeated a system similar to this.
The problem with passphrases is their entropy sucks. If you go ahead and the idea is you're still taking 64 bits out of a random number generator. Passphrases, even because English is incredibly patterned, right? So you got 1.3 on a passphrase. You basically are talking about sentences, meaning you only hit 1.3 characters per 1.3 bits of entropy per character. So, that's the average for English. So let's say you have a 40-character passphrase. You're still only talking about 50 bits of entropy, 52-ish. Most passphrases aren't even 40 characters. Most of them that I've seen are something like 20. So you're talking like 30 bits. So your passphrase breaking was based on the fact that people select crappy passphrases. And the reason people select crappy passphrases is because that's all they can remember. Normal sentence recollection is pretty weak, just like talking about with storytelling. Our ability to remember the precise details of stories is pretty weak. But we have hardware acceleration for names. And so because you have hardware acceleration, the theory, and this actually does require, a greater sample size than my head, the theory is that that our capacity should be much larger for these. Go ahead.
There's actually a site that I can't quite remember the full URL I'm working for, but it's called Diceware, and it actually